Okay, so for the quick return property of mechanisms, we can investigate how uh how the forward motion and the backward motion are in relative with each other. So this might be important for a lot of reasons because let's say you want to use a shaping machine, you want it to be slow in forward and then in backward it should be fast, no? So you won't have to wait a very long time for let's say for the shaper to come back before it gets the motion that you are trying to find, no? So the quick return property is just the ratio in between the time of the forward motion versus the time for the backward or the return motion. So we can usually measure that QRR based on their angles, no? So in this case, the forward motion will be this angle right here, no? Actually, this should be clockwise, no? But anyways, so this angle right here is very slow, no? As you can see, it has if this is 360, then it is more than 180 degrees. Okay, and then the return motion is just this right here. No? So we cannot take the longer time, usually the forward time, beta, and the return time as alpha in terms of the degrees or the angles. So again, QRR is just a ratio between the forward motion over the return motion in terms of time, or in this case, in angles. Although, in the important part of this topic is that you have to know that the QRR doesn't really depend on the speed, no, or the angular speed of the mechanism, and usually it is dependent upon the configuration or the sizes of these links, no. So the direction of the rotation could be also in effect because the QRR might get lower if you reverse the speed or if you reverse the direction of rotation. Okay, so another one is that there are cases where we have an even return mechanism wherein the forward motion is equal to the return motion time. So let's discuss now this slider crank mechanism. So you have this basically a slider crank, and let's say you want to find the maximum length of the stroke. So this might be important in internal combustion engines wherein we want to determine what is the stroke, no? So to determine the proper design for the volume displacement of your automobiles, you have to properly size your mechanism. So in this case, we can determine the two extreme positions to be this and this. So how did we determine that again? So if you have this first extreme position, just remember that your crank here, your crank AB, should be coincident with the connecting rod, no? Which is BC. So if that is the case, this is the one extreme position, and usually the leftmost side, no? And then for the other one, so the other extreme position will be from this one to this one, no? So as you can see, this case, the link AB and BC are fully straightened out, no, and collinear with each other. So these are the two extreme positions. We can determine their displacement, no? So you can use the graphical method, you can draw this and then find the position where it is coincidental or collinear. Then you can find this length here. You will have a graphical answer. But we are again very interested with analytical answer right now. So we want to find this or sorry, for this example, we want to find the stroke of this slider crank mechanism. So we have a given AB, BC, and the E, no, or the offset. And actually, the 60 degrees is irrelevant here. Maybe this is just a starting position of your slider crank. So it is not really important. We only need AB, BC, and E. So we have to first check, no? We have to make sure that this is a Grashof mechanism. We have to make sure that AB can fully rotate. So we can check first if it follows the Grashof's criterion. So you can add the shortest length in the offset, and this should be smaller, you know, than the other lengths. Okay, so as you can see, this follows the Grashoff's criterion. Therefore, the crank AB can fully rotate. Now, to solve this, you can really, again, you can just find the coincident and the straight line, no, or the fully straightened out crank and the connecting rod, no. And you can do this graphically. You can solve for this stroke 46 centimeters and this quick return ratio 1.26 by measuring. Now you can use your rulers if this is in ratio, no. So you can find this stroke, and then you can also find this alpha here, and then we have this beta using your protractor. But anyways, we are interested in the analytical approach, so let's solve this in an analytical way. Okay, so where is it? Sorry, I couldn't find the new slide. So just wait a new slide here. Okay, so we can imagine your I think I'll just create this one so that it is easier. Excuse me for a while. Okay. So yeah. So for this example, as you can see again, we have this first extreme position and this other extreme position. So we can find this maximum stroke, no? So the way that we can solve this, we can use again what we've used so far, trigonometry, to solve for this length. So as you can imagine, we can find this stroke right here, no? By finding the length of this triangle here, this right triangle right here, and also the length of this right triangle right here, no? So you can see, or just this one. So you can find this length right here, and then find this length right here, and then subtract these two lengths, you can find S max. So if this is S max, the maximum stroke, you can, let's say, find X prime and X double prime here, and you can subtract, no, this two. So S max is basically just this X double prime minus X prime. Okay, and we already have this stroke. So to find this, as you can see, these are all given, no? So this is given, no, right? So you have a triangle here. We can start with this first, no? We can start with this other extreme position. So you have here A, you have here B double prime, you have here C double prime. So the length here is AB plus BC basically. So you have 20 plus 65, which is 85 centimeters. And then actually, you also have the offset. So the offset here is also determined to be 30, no? So the distance here actually is 30, no? So from the frame A to the line of stroke of this link C. So this is 30. We can determine this x double prime. So you can use Pythagorean theorem to find x double prime. So x double prime is just the square root of 85 squared minus 30 squared. Okay. And then for the other triangle here, as you can see, this is also a right triangle. So we can notate this one. So this is point A, this is C prime, and then right triangle. We know this length is, so this length here is the difference between AB and BC. So we can write here 65 minus 20, that is 35, no? And then for what is also given is the offset. So the offset here is the same as well. So you have 30 in here, no? So you can use again the Pythagorean theorem. So you can determine x prime. So x prime is equal to 35, sorry, the square root of 35 squared minus 30 squared. So solving for that, x double prime and x prime, and then you can solve for x max. So let's compute that. So you have 85 squared minus 30 squared. Sorry, 30 squared. So this will be 79.53. 79.53 centimeters. And then for x prime, you have square root of 35 squared minus 30 squared. So we have 18.03. So correct. This should be 45, right? Sorry. This should be 45. Okay, so let me just correct this one. So this should be 33.54. 33.54 centimeters. So therefore, the maximum stroke is the difference between the two. So you can just subtract these two values. So the answer is 45.99 centimeters. So this will be your final answer. Okay. So we can also determine the quick return ratio. So how do we determine now the quick return ratio? No? So to determine the quick return ratio, what is the forward motion? No? So usually the forward motion will be the smaller angle, no? Most of the time. But it could happen that it is not a quick return, no? So as you can see, this should be your alpha, right? And then this will be your beta. So therefore, your quick return ratio is just the the beta over the alpha. Or if you want, you don't have to solve for the beta. I can just say, so as you can see here, I deleted it. Sorry. So as you can see, beta and alpha are or their sum is 360 degrees or 360 degrees. So you can also say that beta is equal to 360 minus alpha, or alpha is equal to 360 minus beta. So there are cases where you can use 360, sorry, beta over 360 minus beta, or you can also use 360 minus alpha over alpha. So for this case, I guess we can use this one. We can just find this alpha right here. So to find this alpha, we can see this analysis now. We can create an analysis in here. So you have A, B here. So you have A and then B prime. And then you have A and B double prime. So this will be your x-axis and this will be your y-axis. So this will be 90 degrees, right? 90 degrees. So I think we can solve also for their angles here. So the angles here can be determined for A, so A double prime, and since this is what we can find, no? This is theta A double single prime. We can also say, since they are vertical angles, am I right? Are they vertical angles here? Oh, so this should be not that one, no? This should be the B prime. So they are vertical angles. So we have theta A here. So this is also theta A. And this will be theta A double prime. Yeah. So as you can see, the alpha is the total angle here. So you can say alpha is equal to theta A prime plus 90 plus theta A double prime. So you can solve for this too. So you can use again the trigonometric functions now, no? So in this case, we can use the sine, no? Sine law. Or not really the sine law, but the sine function. You can say sine theta A prime is equal to 30 over 85. Okay, and then for this one, you have cosine theta, this should be double prime. Okay, cosine theta A prime is equal to 30 over 45. So, rewriting this again, you have theta A as, this will be, so let me just do this mentally, So, our cosine and then 30 over 45, plus 90 plus you have inverse cosine 30 over 85. Okay, so alpha is equal to okay, I can solve this one. So shift cos 30 over 45, 30 over 45, and then plus 90 plus arc cosine or inverse cosine, so 30 over 85. So the answer is 207 degrees. Let me check if this is, so why? I think we have done an error again. We have an error. Oh, if we use cosine for both, it should be sine for this one. Okay, my bad. So we change this one. Shift sine. So you have 201. What did I do? Oh, so the other one should be sine. My bad again. So this should be shift sine. So 158.86. So we have 158.86 degrees for the alpha. Now to find the Q or R, we can just use this one so that we can directly solve this one, no? So that the Q or R can be solved. You have 360 minus 158.86 over 158.86. So the answer is 1.266. So 1.266 is your quick return ratio. Okay, so that's it.